What's up, everybody? This is Matt Brown. Today, we are taking a look at an AT&T LTE router that has been locked down. AT&T does not want its users to be able to configure and control this device. But by the end of this video, we are going to take control. And so we're going to give the power back to the users today. And let's go over to my screen and show the problem, because it's not just me that's noticed this. I'm not a customer. I just found this device in an e-waste bin, but I have seen, while I was searching for the web application credentials for this device, a number of users complaining that they cannot log in to the web interface on this router that they purchased. They're AT&T business customers in some cases, and they are asking, they're saying, hey, like, I want to change the wireless settings on this device, and AT&T coming back and being like, oh, well, the password's on the back of the router. No, the Wi-Fi credentials are on the back of the router, not the credentials for this login page that you can access from being on the Wi-Fi network or being plugged into the Ethernet port like I am. Being on the LAN side of that network. Normally, if you own a router, you can log into it and make changes, but AT&T has developed a very specific firmware. AT&T, they didn't develop this router wholesale themselves. It's a data remote made router that they have some custom firmware configuration loaded onto to make it lock down so that their customers can't get into this device and mess with its settings. So we are going to attempt in this video to get back control of this device and figure out the login credentials, the username and password to this system, right? And you'll notice in some of these forms, so this person is asking about this device. They're saying, hey, I tried, admin, I tried a lot of common obvious guesses. This user over here really did their research. This is a more up-to-date version of this router, but very same situation. There is this note of a DRI admin, some more custom username, password they're trying to guess. And these seem to be the default passwords for the default firmware, the kind of original OEM firmware that this router manufacturer makes. But again, AT&T has a custom firmware or a custom configuration that they've loaded onto this device to not let their users in. But we're going to see if we can go over to our desk and if we can figure out a way to let the user in. So with that, I'm going to pop over to our desk cam, and you can see that I've already I've popped the top case off of our router, and we're just going to take a look around. So I open this device up as a hardware hacker. I immediately recognize some components. We have a CPU, we have some DRAM, your volatile memory. Over here we have a flash chip of some kind. And what's interesting, if you're only used to being inside of standard Wi-Fi routers that have Ethernet and wireless networks, this may be new to you. So this is a cellular modem, and over here is the SIM card slot. So this device has the capability to either have the internet be from cellular, or it actually does. I don't think anybody uses it. It has POTS connections here, and I don't think in the AT&T configuration they support the like DSL or POTS phone line method of getting internet. I'm pretty sure they only support the LTE method, and so that is going to be the standard use case. And so that's kind of a cool thing that I definitely want to go down that rabbit hole in a different video, but we're going to kind of ignore the LTE portion of this router today. We're just going to try to gain access to that web interface. And so looking around this device, my eyes are immediately drawn to these pins right here. There's actually 5 of them. Oftentimes you'll see a set of four pins, but I did not even solder these these pins, these connectors in here. They were already nicely present like that for me. And so what I'm going to do is I'm going to assume and then verify that that is a UART, a serial connection to the underlying system that will allow me to interact with it if I know how to speak that serial protocol. So the way that I'm going to try to find that first is I'm going to power off the device. You can see those LEDs go out there. I'm going to put my multimeter here into continuity mode, and I'm going to hit it to the audible mode so that when I make a connection, I get that, that audio feedback from my multimeter. So first thing I want to do on a device like this, I want to find ground. It's really easy to find ground on devices like this. Any of these shielded components, so I can verify that these shielded components are grounded by just touching two of them. And I get that beep. So now I know I can hold one of my multimeter probes there. And what I want to do is I'm going to assume that there's going to be at least one of these pins that is ground. And finding that, like I said, I can find a connection to ground in a lot of places on this board, but I want to eliminate these pins, some of these pins, as candidates for two signals. One is TX and the other is RX, transmit and receive. And so what I'm going to do is I'm going to go probe through here. Okay, I get a beep. So this is a ground pin here on the left. Nothing, nothing, nothing. And that is grounded as well. So the left and the rightmost pin in this set of 5 pins are connected to ground. So now what I'm going to do is I'm going to switch over to voltage mode. Gonna again just hold here. This is an easier spot to hold for my ground. And now I'm going to go and I'm going to click the button to turn on my power strip that's going to power this device. And then I'm going to measure the voltage on these 3 pins in the middle to see if I can find the board's transmit pin. The way I'm going to ID the board transmit pin is that if it's transmitting data, I'm going to see this voltage fluctuate, not be constant. And so here we go. I'm going to hit the power, probing. Okay, I don't see anything there. There we see 3.3 volts, and there you see that. You see it's dropping down below that high voltage of 3.3 volts. Okay, so that is most likely a transmit pin. I'm going down the line again to the next pin. This is holding steady at 3.3 volts. Okay, so this is great. So I have one pin that was kind of floating around 0, one that was going back and forth between 0 and 3.3, and one that was just a solid 3.3 volts. So that tells me that that middle pin that was fluctuating is definitely the transmit pin. And then I'm going to guess that this, the pin that is to the left of center is our receive pin on the board, where we want to transmit data to it from our USB cable. So what I have here is just kind of a standard UART USB cable here that has, it actually has 6 wires here, but we are only going to use 3 of them. We only really need 3 to interact with most UART systems. We're going to need ground, transmit, and receive. So first what we're going to do is connect up that ground to one of those ground pins. I'm going to do the one that's all the way on the right. And then we have our yellow and orange on this cable. You're going to have to look at the pinout of your specific cable. So on my cable, the yellow wire here, which then is connected to this green wire up here, I probably should have color matched those, that is our receive pin on the cable side. So what I need to do is I need to connect the cable's receive pin to the board's transmit pin. And so we're going to do that. We guessed it's that middle pin. And then I'm going to make that other educated guess and connect the transmit pin of my cable to my candidate receive pin over here on the board. So now I've got our 3 signals, ground, TX, and RX, ready to go. And I'm going to get over to the computer. I'm gonna turn the device off. And we're gonna get ready to receive these signals. Okay, so over here I have my command ready. I'm going to use picocom. I'm going to guess the default baud rate, which is like in 95% of the cases on these modern Linux devices, it's going to be 115/200. And then on my Linux system, when I plug that USB cable in, that other end of that UART adapter in, to my system, it's going to show up as dev tty USB 0. So now I've got that open. We're going to head over here. And we're going to watch what happens when we power on our device. So we're going to see a bunch of output come along. It's going to pause here for a little bit, and then it's going to continue to boot. I'm actually going to scroll up so that it doesn't scroll down on me. So the first thing that I see right here is it says, please choose the operation, and look at option number 4 there. So it's telling me to like press number 4 if I want to enter boot command line interface. That is very useful. That will allow me to pause the boot process the next time around that I reboot the system. That will allow me to pause in the bootloader and potentially have access to the bootloader where we can do things like change configuration of the boot process, maybe read some of the flash data, things like that. So now I'm just going to scroll down here. Kernel command line. This is always really good to note. I'm actually gonna take some notes. This is what I usually do. My hacking process. I'll just open up a little text file here. I'll take some notes as I go along. Okay. So the kernel command line is very useful. Right here, it looks like I'm getting, it's printing out stuff, but if for some reason it was like, it completely went dark on you, that might be because of something in the kernel command line that is causing that to happen. So it's always good to know what's happening there. I'm going to scroll down some more here in the boot process, and I get to this. This is always super helpful and something you'll often see printed out in the UART shell when the Linux device is booting up. This is the partition table of that flash chip that we identified over on the board. And so we can see the address start and end addresses. And that is very useful if we want to read the contents of those partitions out of flash and extract those somehow. So we're going to keep scrolling down. There's a bunch of information that we could look at. So here I see something very interesting. It's calling the change password command, and it says password for superadmin changed. Okay, so this is really interesting, and again, maybe matches some of what we might expect the system to do, right? If there is some kind of customization that AT&T has on this system to set the password to some not usual, non-default, default password, maybe it's doing it in this boot process, right? So this is very interesting. It says, and we have an indication, maybe, that this superadmin is a username, that is actually the username that we need to be entering, into this web interface, right? So all really cool stuff to note. So I actually want to get back into that bootloader menu and see what I can do in there, because you'll notice here, I hit enter, I'm not even getting a login prompt, let alone like a shell or anything. So I can't really do much with the system in this state after it's already been completely booted. But we're going to remember that it told us that if we hit 4, we can potentially get into that boot menu. So I'm going to power the device off, on again, and then I'm going to get over here to my keyboard. Like smash something over on my desk. All right, but we have successfully gotten into the bootloader menu. So here, we'll ask it for help, right? That's always a good place to start. So you'll recognize right away if you've done this kind of stuff a lot, right? That this is U-Boot, right? Probably a heavily modified U-Boot. A lot of device manufacturers do that. They'll take the open source U-Boot project and fork it. So U-Boot is a open source bootloader that targets Linux systems like this. And so you'll see here we don't have a lot of commands. If you've watched my other videos, you'll see that sometimes I'll get into a U-Boot shell and there'll be like 50 or 75 commands that are available. Here we don't have that many, but I do see one that again corresponds with what I saw on the board in relation to that flash chip. So SPI is a type of flash storage. And so if I type, no, that's not the command I wanted. If I type SPI, it'll say, well, it'll say, hey, you need to write help SPI. Okay, so here are some of the subcommands for this SPI thing. I can run the ID command, which, you know, just tells me ID of the chip. I really don't care. But there is this SPI read command that is very interesting, that takes two arguments, an address and a length. So let's see what this does. So if we just read from address 0 and let's throw in like 10. Now, something I noticed right away, because the documentation for these commands is oftentimes like incomplete and terrible, so you just have to experiment with them. A thing to note about this command, if we're going to use this for anything, is that it is parsing that last argument in hex. Even if I don't do 0x in front, 10 in hex is 16 in decimal, right? And it's even telling us here, read length 16 when we put in 10, right? So that's good to know, that any kind of length that we're going to specify, we're going to have to convert that to hex. So let's do that. Let's see what we would want to read from these partitions, right? So definitely the root file system would be something that would be interesting to pull off this device, but my mind actually goes first to these two config partitions. Those seem to me to be very interesting, just because you'll often see devices that are configured that have sensitive things inside of some writable configuration partition, where oftentimes the root file system might be a read-only partition where any kind of changes to a password or a credential or anything, they're not stored there because that file system is intended to never change throughout the life cycle of the device. So we're going to prep this command, but first, first let's look around. Okay, so this SPI read, so let's do SPI read, and so again, so this is the start address over here. So let's just take a peek at this config partition, right? Let's just read like 100 in hex, whatever that is, 256. That's what it is. Got to know your hex. So that's boring. That's just a bunch of Fs. Okay, let's try this config underscore back partition. Let's see if there's anything in there. SPI read. Okay, that address, and then 100. Okay, now this looks like we've got some good data in here. So that config back partition is interesting, and I think it warrants us pulling the whole thing. So to do that, we're just going to kind of write out what our command is going to be, and then we'll paste it in. So we're going to do SPI read. And then, okay, so we know our start address. That's here. Now we need to specify the length of this. So I'm going to open up a Python shell, and we're just going to do a bunch of math here really quick. So what we're going to do is we're going to take the end address, and we're going to subtract it from the start address of our partition. And then what we're going to do is we're just going to say, let's convert that to hex. And just like that, we have our command ready to perform our read. So we can get rid of our Python shell for now. And, oh, okay, yeah. So what I'm going to do is I'm going to exit out of picocom by hitting Control-A, Control-X really fast. And what I'm going to do is I'm going to add an argument here. I'm going to say -- log file, and we'll just call it out.txt. So what this is going to do is all of the inputs and all of the outputs that happen over this UART shell are going to be logged into this text file. So when our command, when our SPI read commands prints out all of this hex, it's going to get written into that file. Now, it's going to be in a weird text format. It's going to have all these like white spaces in the middle. So then we're going to have to parse it. But this is what's going to allow us to read this entire firmware, or excuse me, this entire partition out of this system over UART from the bootloader. Okay, so we are going to issue this SPI read command, and it's going to start scrolling. In the meantime, we're going to open up a shell here. I think that's where we are. Good, good, good. And we will wait for that to complete. Actually, in the meantime, so what we're going to do is we're going to write, okay, we have to move that to demo 3, and then let's go to that directory. Okay, so now I got a couple terminals, and we've got this text file here. So let's actually just go look at this text file. Okay, so we can see my command, the first line of output where it says read length, that tells us how many bytes it read out. And I'll hit down one more time, and then all on one line inside this text file is every one of these hex bytes printed as a string, right? So what I'm going to do is I'm going to clean up this file first just to make it easier for us to write a parser that's going to extract all these bytes out and convert them into their binary form. So I'm going to delete these first two lines, and then this little like, $M thing, I'm going to hit X in Vim to delete that. This line at the end, I'm going to delete that. So now all I'm left with is the data. And we're going to make an observation about the data right here is that you'll see that the way this U-Boot output of this hex dump works is that if there's a leading 0, it just doesn't include it in the byte, right? So here's this byte that would normally be represented as a hex byte as 0, 1. It just lists it as 1. So we're just going to have to be aware of that and account for that when we write our parser. Okay, we'll save that file, and now let's write some Python code together. Okay, this is just going to be some really quick and dirty Python code today. So we're going to have a file name. Well, let's call it like, in fname, and we'll get that from the command line, the first argument. And then we're going to write this out to a file too when we can do all this data conversion. So we'll do argv2. So in case you're wanting to understand how that's going to look, so we're gonna call our code like this, and so it's going to take in that text file, and then we'll call it out.bin. So we're going to run our code like that, and so this out.txt is going to be put as in fname, out.bin is going to be out fname. So now what we're going to do is we're going to open, we're going to like open those files for reading and writing. So this in file, we're going to call fin, I'm going to say open, and we're going to say, we're just going to do R. So we're just going to read from that file, and it's all text data. So we don't need to put the B permission in here for binary. And so then we're also going to do fout equals open out fname, and here we are going to write and we're going to specify that B, because some of the data that we're writing out is going to be in binary format. It's not all going to be text. So we're going to need to do that. Now we're going to say for line. There's only one line, but this is just, I'm like doing it the quote unquote right way. For line and fin, then we're going to say line, let's say like data equals line dot split. So what I'm doing with split is by default, split, if you don't specify any arguments for that function, what it does is, that's my multimeter yelling at me to turn it off, save battery. So the split function, it will split on white space, and it'll strip out all white space to either side, which is perfect for this use case, right? Because everything is separated by white space. And so what I'm going to do is I'm going to call that, and then I'm just going to print this out. I always like to do print statements and just slowly build my Python programs. So here you'll see now we're dealing with that data variable is an array of strings that represent all those bytes. So now you remember we have to deal with that case where I said that some of the data doesn't have that leading 0. So what we're going to do is we're going to say for d in data. So we're going to go through every one of these bytes now. We're looping through every byte, and we're saying if the length of that byte, of that data byte, is equal to 1, then what I'm going to do is I'm going to say d equals 0 plus d. I'm going to add a 0 to the beginning, and then back outside of that conditional, we're going to say, actually we're going to say like out data equals bytes, and then we're going to say out data plus equals bytes dot from hex d. So we're converting each individual string representation of a hex byte. We're converting it to a bytes variable in Python, and then we're appending it to our ever-growing list of bytes. That becomes out data. So then we can, I mean, if we want one really quick sanity check before we finish this program, it would look something like this. And probably gotta hit less to make it look interesting. Okay, so now you're seeing that like string data there. That's coming out of that, and then the final part of this is going to be to write it to this output file. So we just do fout.write out data. And we're done. So now when I run this program, and it's not gonna, this program doesn't have, okay, I got rid of all my print statements, which is good. I run it, there's no output because what it is doing is it's writing the file out to out.bin. So now I can run strings and I get a bunch of data out of that stuff. So now we have successfully, completely pulled out of the bootloader that entire partition using that spy read command, and now we've written just a really simple Python script to convert that hex dump format back to the raw data. And we see a lot of interesting stuff in here. And this is where it gets really fun because now, let's get rid of this source. Don't need that anymore. Exit. So we can run strings out.bin. I don't know. You think there'd be any like users or passwords in there? Well, there are. So, so before, remember there was that super admin, right? So here we can see the admin user configuration is set to super admin. Well, that's pretty interesting. And right down here, we see super web password is set to this value, which honestly we never would have guessed. We never would have been able to brute force it, but for the hardware hack, we would not have this credential. So let's go and try it on our web interface. So let's try super admin, paste that password. and no route to host. Oh my gosh, that's because the device isn't on. Wow, that was anticlimactic. We have to reboot. We have to boot into the device. We were paused in the bootloader. That's why it's not working. All right, so we're pretty sure this is gonna work. But what we can do in the meantime is we can get ready for the next part. So let's just track when this device comes back up online, because we're all very interested for it to be back up. And there's a bunch of other really interesting things in that config partition. It's very, very, very interesting stuff. Multiple different passwords actually in there. So, come on, man. I guess we could kind of like track the boot process of the device. Let's do that. Okay, it's doing things. Yeah. Setting up the bridge interface. Yeah. Come on. Ooh, okay. So, okay, now the system is up. So now we can go back to here, where we can try superadmin and paste our password in. And we're in. We have now logged into the system as the superadmin. We have access. We can go and configure the system to our heart's content now. We could change that default SSID. We could go in and reconfigure the password, make any setting changes we want. But, oh wait, there's more. So this is the web login, but I wonder if we could do anything else with this. So let's go back here. So yes, it's very clearly on the network now. So let's run an nmap scan really fast on this thing. They have left SSH open on this device on the LAN. So yeah, I mean, you wonder like would they really reuse that password for the root log, for the SSH login? Well, they did. And so I don't know, ID, who am I? Whatever, I'm root. I'm actually superadmin is what I am, is the only user on the system, but the superadmin is UID 0 on this system. And so now I can run this. Of course, it's BusyBox, so we just literally just run PS. There we go. We can see what's running on this system. There's Dropbear, which we're very thankful was running on the system. Dropbear is a lightweight SSH server, excuse me, not a client. And we can now have full control, like completely full control of this device. We could really do whatever we want to with it. And it opens up a lot of interesting things you could do because this is an LTE device. You could think of all sorts of fun applications that you could use this router for. The interesting thing about this router is it actually has the battery packs that you can load massive batteries in here and not have it powered by the standard power, AC wall jack. And so you could actually have a rooted LTE device that you could carry around with you and do all sorts of fun things. And there you go, AT&T. You tried to keep us out, but we got in anyway. Want to thank everyone for watching this video and just seeing my process, right? I hope you'll see that I make mistakes along the way, just like you do when you're probably exploring this or learning something new. But if I can do it, you can do it. So thank you for watching. Let me know in the comments if you want me to keep doing content like this. Thank you and have a good day.